Hello, and thanks for having me at this year's OPC Days International. I'm going to present you today an overview of activities and harmonization in the field of mechanical engineering. My name is Herden, and I'm working at the VDMA since about 5 years now, and my specific role is the OPCUA coordination and harmonization of the different working groups. So, first of all, why are we doing this all? We have a target image which you might know pretty good from personal life. The target image is to create interoperability. So for example, if you buy a computer mouse and you connect it to your computer, it will just work. Or when you buy a cell phone which supports the Bluetooth standard and you have a car which supports the Bluetooth standard, then you can just connect it and it will work. So this is called plug and work or plug and play. And that's something we want to achieve in the industrial context as well, because there we have different machines from different domains working together. And in the end, it takes a lot of effort to make them work together. And with interoperability, we can lower this effort and create new possibilities as well. So how do we do this? We want to achieve interoperability. So I brought this graph, and we're coming now from Industry 3.0, where we have proprietary communication, but we're entering the field of Industry 4.0. And here the first step is to get all the different systems, machines, and components into one meshed communication network. And for that, we use OPCUA. We use OPCUA because it has several advantages, like it is open source, it has security built in by design, it supports various protocols for server client, for pub/sub, it supports semantic machine descriptions, and I guess that's the most important point for us, and it also is highly scalable from an edge device up to the cloud. So we have OPCUA, which defines how the data is transferred, but it doesn't describe the data itself. So what we need is a description of the data so that we can make use of the data, that it really becomes information. And so we define so-called domain-specific harmonized information models, and these are called companion specifications. In the VDMA, we now have already published more than 60 different companion specifications. I brought you this graph so that you can get an idea of all these companion specifications. In bold, you can see the machinery specifications, which are the most important, as I will show you in the next slides. But you can see there's a lot of other companion specifications for robotics, for cranes, in the field of plastics and rubber, machine vision, weighing, and so on. You can read it here. And on the right side, you can see that a lot of specifications are still coming up, that we have a lot of active groups working on the topic of OPCUA. And now to give you an update on what happened this year already in 2024, you can see that we already published specifications like the energy consumption management. We have already seen this presentation, like the job management presentation from machinery, a new version of machine vision, of weighing, of flat glass, joining and tightening systems, a new version of machine tools, metal forming, cutting tools, laser systems, woodworking machines, the mining external standards, and the process air extraction and filtration systems. So even the groups that already published something still bring out new and better versions of the companion specifications. On the other hand, we have upcoming groups that are started in 2024. We will create a specification building block for OPCA for machinery for energy management based on the energy consumption management we have just seen. We will have a new group for battery production. We have a new group for cleaning and pretreatment machines, for electrolyzers, a group is about to start, for foam cutting machines, for conveying in the field of mining, for particle form machines. The Weihenstephaner standards will be extended for sweets and baking, and we have the wireless machine tool peripherals, which started this year. And this is an overview of all the different VDMA domains. So I colored the domains that already published the specification in blue, and I made all the domains that are working on companion specifications but didn't publish something yet in orange. And as you can see, it's a very colorful picture, and if you are following us, you will recognize that the picture is getting more and more colorful and especially more blue, because it's really a topic that is driven in all the domains. And almost half of all the companion specifications within the OPC Foundation come from the field of mechanical engineering. So this is really the second step to achieve the interoperability. We have OPCUA for the technology, how the data is transferred. We have the companion specifications for the domains, which describe, for example, for a robot, how the information should look like in the server. But what we realized in all these different domain-specific groups is that some information is the same for all these groups or for a big number of the groups. So for example, information like who is the manufacturer of a machine, when was the initial operation date of the machine, what is the current status, what's the current power consumption. These are very, very basic information that we thought need to be modeled in the same way so that we get interoperability not only within a domain, but also cross-domain. And that's why we started a group called OPCUA for machinery. And in OPCUA for machinery, we also define a companion specification or a series of companion specifications which define specific building blocks for use cases. And we already have published building blocks for the use cases of machine identification, component identification, machinery state, process values, result transfer, counters, and job management. And of course, we are also working on new building blocks at the moment on basic server structure and, like I told you, energy management. So OPCUA for machinery is a series of companion specification, and it can be used as a standalone model. So for example, if you come from a domain which doesn't have any companion specification yet, you can still use OPCUA for machinery for the generic information to be interoperable with all the other domains that also use OPCUA for machinery. So machinery can be used as a standalone model, but it can also be referenced as base specification. And that's what already is happening. So for example, if you take a look at the interface of a laser, you will see that the machinery specification, the machine tool specification, and the laser specification is used. Or for example, the interface of a woodworking machine. There we will find the machinery specification and the woodworking specification working hand in hand. And if you are an end user, you just need to look into your domains. For example, if you are a laser machine builder, you check out the laser specification, and within the laser specification, there's a reference to machine tools, and within machine tools, a reference to machinery. So you really don't need to be an expert for all of this, but you can be sure that we try to achieve harmonized interfaces also in cross-domain context. So OPCUA for machinery, as I mentioned, is a specification series, and the already mentioned building blocks are divided into different documents. So we have the part 1, which contains the basic building blocks. Then we have the part 2 for process values, the part 3 for job management, and the part 101, because that's a bit more specific and most likely not everybody will need it, we have the result transfer. And of course, even in the harmonization of machinery, we try to harmonize. So it's a harmonized approach. And for example, the basic building blocks uses the part 100 devices a lot from the OPC Foundation. Or in process values, we use PADIM. Or the latest example would be job management, where we try to define our own job management model, but we found that the ISA 95 job control model can be adjusted to our needs. So we collaborated with the ISA 95 group and they adjusted their model, and now we are using ISA 95 job control. So let's take a look at how OPCUA for machinery can bring you benefit. So I brought two examples. One example is the machinery state and one example is the job management. And for the machinery state, we came from the problem that everybody had his own states, its own names for the states. And so it really was everything but harmonized or interoperable. So we came together as the group and tried to find a solution for that. So before, even for just producing, there were names like working, running, executing, production or special things like dry run. So it was really, really diverse. But now with OPCDI for machinery, we have these 4 states defined as machinery item state. So we have the state of not available, which means the unit is just not available. It's, for example, switched off or in some energy saving mode. We have out of service, which means the unit is available, but it's not functional. So we are most likely in an error or the machine is blocked or something. Then we have not executing, which means the machine is available and functional, but is not performing any activity at the moment. And then, of course, we also have executing, which means the unit is available, it is functional, and it is actively performing an activity. And now with these states defined, we already have a great advantage. If we look on all these different machines in a production, even from different domains, it doesn't matter in this case, we will see the state in the same format and we can compare it. And in this example, we know, hey, everything is fine. But that's just the advantage on when you look on the machines. You can also look into the machines. So take a look at the component view, so to speak. And in this example, we have some beverage filling line, which is on a red light, which would mean it's out of service. It is not doing anything. And we might wonder, why is my machine out of service? And we will see now that when we browse into the different components, that the different components, conveyor and injection, are not executing. So they are in general functional, but just not doing anything. But the gripper is not functional. The gripper is in some sort of error. Maybe it's blocked at some point. So now, thanks to this machinery state, I can see which component is causing the whole system to stand still. So another advantage of the machinery state. And now a third advantage is you could also do first KPI calculations. So you want to have the key performance indicator for the machine availability. And you know that your machine, for example, should be producing or executing something for 8 hours. But you collect the states and you will see, oh, 2 hours out of service, 1 hour not executing, and 5 hours executing. So I only had an actual production time of 5 hours out of these 8 hours, which I actually wanted to produce something. And so I would know that my availability after, for example, ISO 22400 would be 62.5%. That's just an example, but now I've showed you 3 examples on how this very, very simple state machine can also or can already bring you benefit. Now let's take a look at job management. In job management, it's all about sending a job from an upper layer system to the machine. The job order could be, like in this example, that we have a piece of wood and the piece of wood should become 4 table legs and a table plate and a bag of wooden chips, for example. So I send the job to the machine. The machine at some point will start the job, will also give me some status change notification. The job will be executed, and in the end, I will have a job result. So I will have this wooden piece worked into the different parts that I want to have in the end. I can store the result on the upper level system, and I can also give the signal to the machine that the result on the machine can be cleared so that the space can be used for other things. How did we approach it? I already mentioned we use ISA 95 Part 4 job control for the how does it all work, the job management, what are the mechanisms, and the what information is exchanged within the job we defined in OPCDI for machinery Part 3. There we, for example, give in information for the job order, like what is the planned start time, what is the job name, of course, what is the required material, how long should the job take in general, how many parts should be produced. Then in between, we might get back some status, and in the end, we get a job result. So we will see what is the real produced material, what was the real start time, the actual stop time. I could also have a bill of material or get some performance information like how warm was my oven when I worked on that part or something. So that's really the combination we use, ISO 95 for how and machinery part 3 for what. And as you can see, we also defined here a state machine. But in this case, this state machine doesn't apply to the whole machine, but it applies to single jobs. And each job has a state out of this state machine. So I could send like 3 jobs on the machine, and each of these 3 jobs will have one of these states. And as you can see, we have the 5 general states: prepared, running, ended, aborted, and interrupted. And prepared is also divided into not allowed to start and allowed to start. And these states really come out of ISA 95. And I think it's pretty straightforward. If you send a job to the machine, it's in prepared, then it will be started at some point, so it will be in running. You could interrupt it, and from interrupted, you can also resume it. And in the end, you will hopefully have a successfully ended job. Otherwise, you could also abort it. And there are also substates defined in ISA 95, which we also added to the state machine. So there's waiting, ready, and loaded in the prepared state, which describes whether, for example, the necessary preconditions have been met or not. In ended, we have the differentiation between the job is completed or the job is completed and also all the data processing of the job is completed so that it is closed and that I can delete it. And in interrupted, we have a differentiation between whether the job was interrupted from inside or from outside with the states of held and suspended. You can use these substates, but you don't have to use these substates. And so in the end, you can see we defined several different state machines and also building blocks, of course, in OPCDI for machinery. And you can use each building block individually, but you can also do a combination of these building blocks. And also, of course, these state machines can be combined or used solo. So for example, I brought here some example machines again. A machine tool might have both the machine state and the job state. And other machines might only have a job state or only have a machine state. And so that's really something that is an important message from me to you, that you can use whatever you need, and each machinery building block stands for itself. So don't be worried when one building block might not fit you or is not necessary for you. You can still use the others, and you can combine them nicely because we took care of that it works together. So in the end, we have productions with a lot of different machines from a lot of different domains, and we will get the information with OPCDI for machinery in the same way. So we get the names of the machines, we get the state of these different systems. We in future will also get the energy consumption of these different machines all in the same way. And of course, this is a great advantage, especially for factory operators that want to do something with these information. How does it work now together with other systems, other approaches, like for example, the asset administration shell? I brought an example here which focuses on energy consumption. So we have a machine at the bottom at the slide, which is really the only data source we consider at the moment. The machine has an energy consumption, and for that it has a sensor. And the sensor for energy consumption is really the only source of truth. We only have that one sensor which sends out the data. But we have a lot of applications that need to have this energy sensor value. So in this example, we could have like an asset administration shell submodel for digital nameplate, carbon footprint, energy monitoring. We could have a system for peak load management or for KPI monitoring. So there's a lot of applications which might use this data point. But our goal is that we only have one interface out of the shop floor to provide this data, because it would really be something like a worst case for a machine builder if he would have to create an interface for each and every application. So we have one data source, but n data sinks. And also in these data sinks, we might need more information from the machine. We might need information from the energy provider, for example, which energy mix did I have so that I can calculate my carbon footprint. Or we might need data out of the engineering or out of the production planning. So as you can see on the shop floor, we see OPCDI together with the companion specification as single source of truth, but the data things can be a lot and can be very different, but they should be able to use this OPCUA companion specification data. And with this, I come to my last slide, the outlook. OPCUA companion specifications really enable a lot of upcoming trends. Because for all of these upcoming trends, you need data out of the production. And whether it is AI, where you really want to feed a lot of data, or whether it's buzzwords like data spaces or product carbon footprint, digital product paths, manufacturing X, digital twin, overall equipment efficiency, it all requires data. And also now the EU Data Act is coming up, which says that if you sell a machine in future which creates data, the user of the machine needs to have access to that data. And the user of that machine needs to know what the data stands for. So also here, companion specification is a great help because it already describes all the data and what it stands for and what it means. So you don't have to do any extra work. If you already use a companion specification, then you will be fine for the EU Data Act. You can just tell your customer, hey, my machine follows that interface. You can use the data and a description of all the information you will find in the companion specification. So you can see it's really, really worth to follow the approach of defining and using OPCUA companion specifications. And with that, I'm at the end of my presentation. I hope that it was insightful and that you liked it. And if you have any questions, of course, you can also contact me per email or per phone or whatever. Thank you very much for your attention and see you at the next time. Bye.